computation of eigenvalues. So what we did in the last lecture, we actually focused on power method or obtaining a dominant eigenvalue for a given matrix. Dominant eigenvalue, which is also known as spectral radius. Radius for matrix A. So A is basically n by n, and dominant eigenvalues basically means that if you know it has got n eigenvalues, and if you take the absolute value of them and arrange them in descending order, so this is the largest, and from there onwards everything goes on like this. There can be some equality sign as well because you may have equal eigenvalues. So this specific eigenvalue, what we call as dominant eigenvalue. So there is no equality sign here. Dominant eigenvalue. And this is also known as spectral radius of matrix A. And we saw that we can determine this by using a specific algorithm where we actually start with random y0 vector of dimension n cross 1. Basically, n corresponds to the size of the matrix A. And what we do thereafter is sequence of matrix multiplications, wherein let's say for k equals 1 colon m, m is your max iterations, let me call it max iterations. Your y colon comma k is equals to a times y0, and then you are going to take the norm of that. So I'm basically writing a specific MATLAB, lines of code, so that will help you to understand when I will show you the code itself. Norm of y colon comma k. So just to make sure that you understand what does that mean, y colon comma k basically means the y is a specific matrix, and y itself is basically a matrix of size zeros n comma m, where basically means y is a matrix which has got the dimension n. So it has got, so each vector, so let's say this is y1, this is y2, like that, and you have to go till m. M is basically corresponds to the max iterations. M is equal, and this is n cross m. So you are basically initializing your y vector beforehand. There are certain chat questions.
Professor, can you explain the colon again?
I'm sorry. So basically a vector, n-dimensional vector. Each column is an n-dimensional vector. This is n cross 1, this is n cross 1. So each one of them is an n cross 1. And you are just initializing the zeros for the y matrix. And then when you are doing the loop, you are basically saying that for every increment, you are populating that y vector using this matrix multiplication. So when you multiply A with y0, y0 is a random vector of n cross 1. When you multiply this with y0, you will get another n cross 1, and that is basically getting stored in the kth column. That's what it is saying. Does it make sense?
Yes, thank you.
Okay.
So you're storing an entire vector within another vector, multiple vectors within a vector.
Multiple vectors in a matrix.
Or in a matrix, okay.
Yeah. So matrix is composed of vectors, column vectors. So I'm just populating the column vectors using this computation. So I'm just giving you some of the way the MATLAB I implemented the script in the MATLAB. So just that's why it will help you to understand that what I'm doing in this case. So till now, everybody's good so far?
Yeah.
So then what we actually do is we calculate the eigenvector mu for kth iteration, and that is given by y colon comma k transpose A matrix y colon comma k divided by y colon comma k transpose y comma k. That is my eigen value, and my residual vector is given by mu k times y comma k minus a times y comma k. And then I check whether if my norm of this residual vector for the kth iteration is less than epsilon. Epsilon is an arbitrary threshold number or a tolerance number. So I speak it as 10⁻⁻⁶. If it is less than that, then break, else continue. And so I just create a for loop. Oh, there is one more statement here. Y naught is equals to y colon comma k. Okay, so what I'm doing here, so this is basically, I'm multiplying this random vector y0. I'm just selecting a random vector. It can be any vector. It can be a vector from the uniformly distributed number from 0 to 1, or from whatever selection you would like to make. So it is n-dimensional vector, which is non-zero. It should not be that all the elements are zero. That's what you have to take into consideration. So assuming that you got the random vector, then I'm just multiplying this random vector with matrix A. Then I'm normalizing it such that it has a unit norm. So when I just take this vector and divide it by its norm, I'm basically making it a unit norm vector. Then I calculate the eigenvalue, which is y transpose AY divided by y transpose Y. Then I calculate the residual of this specific term, which corresponds to the error. And if the error is less than the threshold, that means I have reached my eigenvalue. Otherwise, I will continue the iteration. But when I continue the iteration, now my y0 will become the previous. For the previous iteration, the y0 will gets updated with the new value of the y vector. And then these calculations can keep on continuing till this condition is reached.
Professor, what does it say before the 10 to the -6?
Epsilon, threshold value. So it is just in one variable, epsilon.
Okay, thank you.
Yeah, tolerance. Let me know if you guys are with me on this algorithm. That's what I'm trying to explain.
Yeah, I understand everything so far.
If there are any questions, please let me know. I'll try to explain again. So the question is the second end before y0 or after? Second end is after y0. So this is for this for loop, and this is basically for this end. So before we actually go to the next iteration for k equals 2, I have updated my y0. So initially I start with a y0 random vector, but later on, once I enter this loop, for loop, I keep on updating my y0 with my current calculation, current y vector. So that basically what I'm doing, I'm just multiplying this y0 with a times a times a times a. And as we have seen that eventually after successive multiplication of this vector with a's, you will eventually get eigenvalue, which will be your dominant eigenvalue.
Professor, is y equals zeros and m part of the code or no?
Yeah, it will be a part of the code. Actually, it is max, not m, it is max iters, which is, it is max iterations. Okay.
I think you have m on the left equal max iters, so it doesn't really.
Okay, so that also helps. Okay. So we can have nm or n max iters, it works. Any questions, guys?
I have a question. How do we pick the random Y0?
So if you have done your homework number 2 and problem number 3, you know how to generate uniform random number, right? From between 0 and 1. So
Okay.
then 10 times and you will get basically a random vector, n-dimensional random vector.
Thank you.
Okay. So what this specific algorithm does, it actually gives you the dominant eigenvalue. Now, this method is, as I said, that if the interest is to only obtain the dominant eigenvalue of spectral radius, you can use this method, and we call this as power method. Now, let me actually go back to the previous lecture slide where I did not use all this colon and MATLAB based scripts. I just write it very simply um, as in terms of just subscripts. Yk plus 1 is a times yk, and then I take the norm, I normalize it, I basically divide it by unit norm of the vector, so make it a unit norm, and then compute the eigenvector, which is y transpose ay divided by y transpose y, compute the residual, which is eigenvalue times the vector minus a times y, and this residual vector will be 0 if this is actually an eigenvalue, because if you see, remember that lambda x minus ax has to be 0. So this is what we are, this residual basically means this lambda x minus a times x. So that's what we are trying to do. For, let's say for this iteration, the residual vector is close to the threshold value. That means I will stop, otherwise I will continue doing this calculation. So this is, instead of writing it in this form, I just wrote the MATLAB in the MATLAB command or MATLAB language. So instead of yk, I'm saying y colon comma k and so on and so forth. Everything remains the same. Is everybody following it so far?
Yes, Professor.
Yeah, any questions, guys? If not, then I probably ask you guys to go through some of the details between this and this statement or these lines to actually see how we are actually getting by multiplying this by itself, by multiplying any random vector by a matrix and continue doing that multiplication, you will end up with this specific expression. I asked you guys to do that. Has anybody looked at that derivation in your textbook?
Yeah, I was looking at it earlier, and I actually had a question regarding the number of iterations.
Okay.
So I understand that as n increases, because of the dominant eigenvalue, the ratios between the lambdas gets smaller
Yeah.
and smaller.
Yeah.
But does that really take into effect, or like if you only have say 2 or 3 values, like shouldn't that influence that more rather than having say 10,000 n values?
I didn't completely follow your question. Can you repeat again? So you are saying the size of the matrix, say, influences this method? Is that what you are saying?
Yeah, I'm just having trouble understanding. Like I get the theory behind it. I'm just kind of not really.
So that since you asked that question, let me actually share the MATLAB screen so that I can show you the actual implementation here, and that will probably help to clear some of the doubt. Let me actually share. So can you guys look at the screen right now?
Yes, Professor.
Yeah. Okay, so what I implemented, if you remember, this is the problem that we were doing in the very beginning of starting this eigenvalues class, or basically this concept. We are taking this specific matrix and we know that we have got two repeated eigenvalues, which is 6 and 6. Right? Remember, you guys? You guys remember that?
Yes.
If not, I can simply run this code, and this specific line, what is this doing? It is what MATLAB has an inbuilt function of finding the eigenvalues and the eigenvectors. So let's say I initialize this matrix A as this this 3 by 3 matrix, which is from example, I forgot the number. It is 11.5 or something. I forgot the number. Okay, so if I use this inbuilt function from MATLAB, so what MATLAB does, it actually produces two matrices, V and D. D is a diagonal matrix where these diagonal elements consist of the eigenvalues. Now here you see, since MATLAB also uses a numerical method, so you all see here that it is not giving you the exact 8, 6, and 6, because since there are numerical errors involved in the computation, so and MATLAB actually uses numerical techniques to find those eigenvalues. So you will see it actually has it aggregates 8, 6, and 6, but not to the exact decimal places. So that's what the eigenvalues are, and the corresponding eigenvectors are obtained like here. So what the MATLAB will think that this is not a repeated eigenvalue. MATLAB will think these are separate eigenvalues, and it will get a separate eigenvector. It does not have to deal with missing eigenvector, just like we have followed in the class. Do you see what I'm saying here, guys?
Yes, Professor.
Yes.
Yeah, so that is what MATLAB does. But now what we are doing is we just implement the power method, which is the algorithm. We actually just saw it. And here I am just defining a specific threshold. I defined a very small number, 1e -8. It can, let's take it at -6. Max iterations is 1000. So I have 1000 iterations basically as a max, and then initial vector, the random vector I generate between uniform 0 to 1. And this basically means it is an n-dimensional vector. So it is basically making sure that whatever the size of A is, which is the length of the A, which is the n, which is 3, it is generating 3-dimensional random vector. And then instead of saying zeros n cross max iteras, I just make it 1. I may use it as max iterations, but for the time being, I'm just using as a 1-dimensional vector, and this size keeps on getting increased inside the loop. So everything else inside remains the same as I just wrote it in the sheet, where you actually start with this first column of the y vector, and you multiply the initial random vector with matrix A. You normalize it, then you find the eigenvalue, then you calculate the residual, and when you check the residual, if it is less than epsilon, then you break, otherwise you keep on continuing. So if I actually run this script, what do I get? So what I will get is that, so V and, let me actually increase this space. So V and D are what the MATLAB has computed. And the second thing thereafter, what we are seeing here, that after 64 iterations, because what it is giving me output is 64, the KK number of iterations. And for that number of iterations, what is the eigenvalue it has found. So after 64 iterations of this computation, it found the eigenvalue as 8.0000 something 66. So it is very close to what your actual eigenvalue is, which is 8. Do you see what I'm saying here?
Yes, Professor.
So, and then also since y colon at that specific iteration level, whatever the y vector is there, that is the actual eigenvector. So this is what the eigenvector is corresponding to the dominant eigenvalue. Now, if I compare it with the actual, you will see that the magnitudes remain almost the same, 0.707. There are negative signs. You will see they are interchanged, but it is negative 0.707, then again 0.707 and 0. And here also you will see 0.707, zeros and 0.707. So essentially it is 1, 0, -1. If you remember that if we have computed the eigenvalue, since we were using exact methods, using finding the roots from the polynomial. So we are getting 1, 0, -1, or -1, 0, 1, whatever that eigenvector was. And here we are basically getting the similar vector direction as we have computed. Does it make sense?
Professor, I have a quick question.
Go ahead.
So the whole point of power method is to obtain the the dominant eigenvalue, but why are we trying to, maybe you mentioned this in previous lectures, but why are we trying to find the dominant eigenvalue?
Okay, so the reason we would like to find a dominant eigenvalue because that is the most significant significant eigenvalue that is of interest. So for example, in some of the techniques, numerical techniques, I probably have shown you. Just let me share the screen back again. So I showed you that when we are doing these iterative methods for linear system of equations, then the whole stability of this system of equation or the solution method will depend on whether the spectral radius of this or the dominant eigenvalue of these matrices is less than 1 or not. If it is less than 1, then only the convergence will happen, otherwise the convergence will not occur. So if you have to quickly check for an iterative technique, this method, that technique is going to converge or not, you can basically check by this dominant eigenvalue of this matrix. So that is one example that why we actually care for dominant eigenvalue. Another example, another point of interest is that these eigenvalues in the dynamical system corresponds to the natural frequency or square of the natural frequencies. And the first eigenvalue corresponds to the fundamental mode. So if you are interested in only knowing the fundamental or the natural frequency, this, when we talk about natural frequency, this is the one, or this is the, we are concerned with the lambda one, not with other specific eigenvalues, because other eigenvalues are called as second harmonic, third harmonic, and so on. But generally the first harmonic basically means it is the natural frequency of the system. It corresponds to the first eigenvalue.
Okay, thank you.
See what I'm saying?
Yeah.
Okay, so
you said if the eigenvalue is less than 1, that's when it converges. Is that correct?
yeah, the dominant eigenvalue, which is the maximum eigenvalue of this matrix, whole matrix, is less than 1, then only this system will converge. Otherwise, this system will never converge.
Okay. Yeah. Thank you.
Yeah. Okay. So that is some of the, these are some of the reasons that why we care about dominant eigenvalue. But that does not mean we do not care about the other eigenvalue, or what are the other eigenvalues in the system. So another eigenvalues that eigenvalue that you can quickly find using power method is this eigenvalue, which is the least of all. So if you arrange the eigenvalues, the absolute value of the eigenvalues in this descending order, so the maximum of that is called as dominant eigenvalue, and we saw we can find it using power method. Now you just taking a slight variation of that, you can find also the least eigenvalue. The least eigenvalue can be either 0 or greater than 0. You guys agree with me? If I have a bunch of numbers and take the absolute value of them and arrange them in this descending order, then the last digit or the last of this arrangement, the last number of this arrangement can be either 0 or greater than 0. Do you guys agree with that?
Yes, Professor.
Yes.
Yeah. So quickly, we can see that if we just use a slight variation of our power method, we call that as inverse power method. So what is inverse power method? Assuming that A is not singular, is non-singular. Non-singular, basically you know that a singular, can anybody tell me what is a singular matrix? How can you quickly can you find a matrix singular? How we can quickly determine whether a matrix is A singular or not singular? Any idea, guys? Anybody from the class can volunteer.
Is that if the determinant is equal to 0?
Yeah, if determinant of A is equals to 0, that means it is a singular matrix. And if that happens, that basically means the least eigenvalue of this matrix is 0. However, if A is non-singular, then we know that the least eigenvalue, the minimum eigenvalue of A is greater than 0. So what we were doing, we were saying that the eigenvalue problem is can be written by this expression. Is everybody with me on this? A is a matrix, V is the eigenvector, lambda is the eigenvalue, the K is the eigenvalue, and Vk again is the eigenvector. This is a specific eigenvalue problem. You guys agree with me in this representation?
Yes, Professor.
So if I multiply with A inverse on both sides, what I will get? This will becomes identity matrix, so it becomes Vk, and A inverse, this lambda is scalar, so I can basically take it at this side. It will become A inverse Vk. Now lambda k, since it is scalar, I can take it in the denominator here, so it will become A inverse Vk, lambda k inverse Vk. Do you see what I'm doing here? So what I'm saying that if lambda is an eigenvalue of A, then lambda inverse is an eigenvalue of A inverse. Okay. Let me know if you follow this much.
I do, Professor.
Any questions from the class? I will appreciate any feedback, guys, because if I don't get any feedback, it basically means I'm just speaking without any, I mean, speaking in without any audience at all. So if you can kindly give me some feedback, it will be highly appreciated.
How'd you get from the from that third equation? Yeah, the third one to the fourth one.
So I take lambda and put it in the denominator. So it is becomes lambda. So this is I put it in the left hand side, and this I put it in the right hand side.
I
So
see.
it comes in the denominator, so it becomes 1 over lambda inverse times Vk. And instead of writing it here, I actually flip the right hand side with left hand side.
Got it. Thank you.
So if you guys agree that if lambda is an eigenvalue for A and lambda inverse will be an eigenvalue of A inverse, then essentially if we apply power method to this, where let's say I represent A inverse as B times a B matrix, and lambda K inverse is, let's say I represent as lambda hat or lambda tilde Vk. So this is, again, I can find a dominant eigenvalue for this using power method. Apply power method to find dominant eigenvalue. Apply power method to find dominant eigenvalue of matrix B. Now, when you do that, what are you going to get is dominant eigenvalue of A inverse or B. So what you are going to get is you are going to get lambda K inverse max. And that is going to be lambda K min, the least eigenvalue of matrix A. Do you see what I'm doing, guys, here?
I'm still writing, Professor. Give me a second.
Yeah.
Professor, what's the advantage of doing this power inverse?
So the advantage is that you will get this specific eigenvalue. You will get the dominant and you will get the least eigenvalue of the system. So as I said that
Okay.
if you are interested to not only find lambda 1, but all the other lambdas, so one of them technique is that you can quickly find lambda 1 and just slightly changing the system, changing this matrix from A to A inverse, you will find lambda n as well, the least eigenvalue.
Okay, got it.
Okay. Now I will tell you how to find the lambdas for in between, and we call this as a deflation technique. So actually the reason I was late in starting the class is I was trying to implement this code and there was some bug in the script and I could not debug it. So otherwise I would have showed you how you were going to get lambda, I mean least eigenvalue using this method as well. So I will continue working on that script and I will post it in the page board for you guys.
Professor, I have a quick question.
Go ahead.
If we determine that the A matrix is singular and the determinant of A is 0, does that mean that the inverse power method is not necessary because we know the least eigenvalue
Yes.
is 0?
Yes. Okay. Yes. So if we know the determinant A is 0, that means the matrix is singular. That means the least eigenvalue of A equals 0. You don't need to apply inverse power.
Okay. Thank you very much.
Yeah. Welcome.
Professor, the dominant eigenvalue, we use it to determine whether it will converge or not. But for the least eigenvalue, what do we use it for? Is there a use for it?
At least I'm not very sure at this point of time what its application is, but I know the application for this dominant eigenvalue. I don't know about this, so sorry for that. I'm showing you about how you can find all the other eigenvalues if you're interested to find them. I mean, if you're interested to know other eigenvalues. Generally, you in dynamic system, you're concerned about the first harmonic, second harmonic. First harmonic is also called the natural frequency. Second harmonic, third harmonic, generally up to 5 harmonics you are interested because those are the dominant modes on which the energy of any system, physical system actually lies. So if you think about dynamics of a system like a beam which has got a vibration or which has got like bending mode or axial mode, we call basically those modes corresponds to these eigenvalues and the eigenvectors corresponds to the mode shape. So generally we are only concerned about first 5 or max first 10 eigenmodes, not more than that. So if your question is what is the significance of this, at this point, I'm not sure what is the physical meaning of that eigenvalue. It is just an eigenvalue of the system, but it is the least eigenvalue of the system.
I got a question.
Yeah.
Back to that MATLAB code that we have earlier. You showed us like the eigenvector function for MATLAB, and it didn't quite work for a defective A matrix, right? Because it showed
it worked. No, it worked for defective because this is a defective matrix, right? It has got 2 eigenvalues which are repeated. So what is your question really? I mean, I didn't completely get your question. You said it does not work for defective matrix. Why you are saying so? Can you come back to your question again? I'm just trying to understand your question.
Oh, because remember we had to find if the matrix is defective, we have to find like
yes.
Eigenvector missing, the V
yes.
missing.
Yeah.
And the MATLAB didn't do that for us, right?
MATLAB will, since it is based on numerical method, so it is not getting a repeated eigenvalue, just like it is not getting 6 and 6 over here. So it doesn't have to deal with 2 eigenvectors for the same eigenvalues, repeated eigenvalues. So that is what it is not dealing with. But in case it happens that numerically, it does happen that these and these becomes exactly the same. In that case, a MATLAB also has to implement the similar script for finding the missing eigenvector. Now,
thank you.
Doing internally, I don't know because we don't know what it is doing internally, but it is, as I mentioned to you at the very beginning of the classes, this class, that MATLAB just takes one of these methods that we are learning and and implements that in the script. So it doesn't do anything different from that. Okay.
Okay, thank you.
Welcome. So we have seen inverse power method and power method. Now we are going to see the last technique we are going to learn in detail is about deflation technique. So what is deflation method? Deflation method. By the way, we are doing chapter number 15, guys, and if somebody is interested to know what are the what topics and which from where we are covering these topics from, so this is basically from chapter number 15. So what deep list method says that, let's say I have got a, again I'm writing the same matrix, which is I have not wrote it down. Okay, let me actually write that 6 1. Well, this is from example 9.5 actually. This matrix 6 1 negative 2 2 6 2 0 1 sorry 0 negative 1 8. So what deflation method says that first apply power method, to find dominant eigenvalue. So you will get lambda 1. Step 2 is construct a matrix lambda 1 to find dominant eigenvalue lambda 1 and also find the eigenvector v corresponding eigenvector v1. So thereafter in step 2, construct a matrix, a new matrix A1, which is given by A minus V1 A1, where A1 is the first row of matrix A. So when you do that, so let me actually ask you guys to go back to your notes and see what is the eigenvector we determined for lambda 1. Lambda 1 was your 8. So what was, so lambda 1 was 8. What was V1? Can you guys quickly look at that and let me know?
Negative 1 2 1.
That was for, is it for the missing or is it for corresponding to 8? How much you said? Negative? So what I am seeing from my
negative 101, Professor.
yeah, I also see the same thing from my notes. So negative 101. So if we quickly do this computation, A is your this matrix A minus V1, which is negative 101, and A1 is the first row of this matrix. Okay, before we actually do anything here, we have to make sure that whatever the eigenvector we get, we have to normalize the first value to scalar number 1. So basically you are normalizing the eigenvector such that the first entry is 1. Normalizing it so that the first entry becomes 1. So if that is the case, then what will happen that it will become 1 0 negative 1, right? It is just the reverse direction of the eigenvector. If the eigenvector is pointing in one direction, if I take multiply with negative 1, it becomes in the, it will point in the other direction, but the direction remains same. It is going this way or this way. Is everybody following so far?
Yes, Professor.
And when you do this, can you quickly do this, guys, for me? If you have the MATLAB code or MATLAB in front of you. If not, we can do it as well here, but it will take a bit more time. 6 1 negative 2 0 0 0 negative 6 negative 1 2, and what you actually get is 0 0 0 2 minus 0 is 2 6 2 0 minus 6 6 6 1 negative 1 0 8 minus 2 is 6. Do you see what I'm doing, guys, so far? Is everybody with me so far?
Yes, Professor.
Professor, I have a question. Once you did normalizing, how the sign changes?
So when I'm normalizing it, I'm just saying make this entry as one, just not -1, but +1. So when I take that as +1, then I'm multiplying with -1, right? Just multiplying it once.
Oh, okay. Yeah, I see. Thanks.
Yeah. Yeah. Is everybody with me so far?
Yes.
Great, thank you. So if that is the case, you actually end up with a reduced matrix, and which is given by this. So this is you call as the deflated matrix. Deflated matrix means you actually end up with a matrix which of reduced dimensions, 2 by 2 dimensions. This is a matrix. This is a deflated matrix. So instead of size 3 by 3, you actually work with deflated matrix, and you apply a power method to this matrix to find the lambda 2. So apply power method to this matrix again. When I apply power method to this, what eigenvalue I'm going to get, guys? So when I get, so power method is going to find the eigenvalue, dominant eigenvalue for this matrix. What are the eigenvalues for this matrix? Sorry? Can somebody tell me what will be the eigenvalues you are saying? I just missed what you are saying. 6. 6, right? That's what you will actually, how, when we actually solved that, we actually got the eigenvalues as 8, 6, and 6. And we actually solved it using characteristic polynomial. We find the roots of the cubic equation, and you found the roots using this. Now here you will see that in this technique, I did not find the roots. I did not even go there. I did not go construct the characteristic polynomial. So roots of the characteristic polynomial. So we were basically finding a cubic polynomial and then finding the roots. But here in this technique, I was not even going to there. I was not even going to create a characteristic polynomial. So I just apply a power method to find lambda 1 and a corresponding eigenvector. I got lambda 1 as 8, excuse me. And I got the eigenvector. Now the first component of the eigenvector, whatever that number is, can be 2, it can be 3, because it's an arbitrary choice. So it can be any number, but whatever that number is, scale it to 1, normalize it to 1. And once you do that, construct this another matrix, which actually does what? It actually creates a 0 on the first row, and you eliminate 0 row, first row and first column. So whatever the matrix you will obtain, that will be your deflated matrix. Apply power method to this matrix, and you will get the second eigenvalue. Then you will apply power method to first and the remaining, and that will be just 6. So you will get 6 and 6 as the eigenvalues, which is just the same as we have obtained from there. Does that make sense, guys?
I have a question, Professor.
Yeah, go ahead.
So if we start with a 4x4 matrix,
Yeah.
our deflated matrix will be 3x3.
Yes, that will be 3x3. So you have to apply power method to 3x3 matrix.
And that will give us all the rest of the eigenvalues?
No. So you have to keep on doing that deflation till you actually reach the. Now here I just stopped at 2x2 because eventually we are going to end up with the last element, which is going to give you the eigenvalue again. So if you have a 3x3, you apply the power method and you get 1. Basically, you will end up with this matrix, and you find the eigenvalue for that. And then you again deflate it. Then you again go back to 2x2, and then similarly you keep on deflating it for every eigenvalue you found.
Okay, and for the second, so if we start with 4x4 and then we deflate it, we get 3x3.
3x3,
and then we
you
calculate
deflate it.
the values. We just take the highest one.
Sorry, come again. What's the last statement?
So when we get to the 3x3 matrix,
yeah, get a 3x3 matrix.
We use the power method again.
Yes, apply power method again to find the lambda 1 for this 3x3 matrix. Deflate it. You get 2x2 matrix. Apply power method to this to get a lambda 1. Then deflate it again, and that's what you will get. All the other eigenvalues similarly.
Got it. Thank you.
So this is basically another technique which we call as deflation method. There are different methods available in literature for numerical computation of eigenvalues, but these are just commonly used. So we are just going through these specific methods to numerically compute the eigenvalues. Does it make sense to everybody so far?
Yes.
Yes, Professor.
Thanks. Transformation plus QR method. So we are not going to look at the details of this technique, but what these techniques does, they actually help to find the eigenvalues, all the eigenvalues of any matrix, all the eigenvalues of any real matrix. Real matrix. So what householder transformation does, let's say you have a general 3x3 matrix. So just like your A here, 3x3 matrices here, or it can be n by n. It converts. So if you apply the algorithm, and as I said, I'm not going to details of the algorithm. If you're using this householder transformation, then what it does, it converts that matrix, a full matrix. Full matrix basically means you have elements all along, elements all over the space. So it basically, you can have non-zero element over here and all across the matrix. But what it does, it actually converts into a tri-diagonal matrix system if the original matrix A, if A is symmetric, or in upper Hessenberg matrix. Upper Hessenberg matrix, wherein the matrix is in the form of like this. So you have diagonal elements, you have all the elements above the diagonal, and you have sub-diagonal, otherwise everything is zero. So you have sub-diagonal elements, you have diagonal, and you have all the other elements in the upper diagonal, but below the sub-diagonal, everything is zero. And that is called as upper Hessenberg matrix form. And the reason that these are required is that after you apply this householder transformation, you transform a full matrix, full size matrix. Full size matrix basically means that you have elements all over the space. So if you transform them into tri-diagonal matrix where you have zeros on the above the super diagonal and zeros below the sub-diagonal, or in upper Hessenberg matrix form, and then you apply QR method, which is basically another transformation method, then what happens that all the eigenvalues will fall in a diagonal basically. So if what actually QR method does, if you guys remember that when we were doing P inverse AP for when A is diagonalizable, we actually saw that our lambdas were all in the diagonal form. Remember you guys, if you were doing that? This is our D matrix. Do you guys remember if A is diagonalizable?
Yes.
If A is diagonalizable, that means I have got P using the independent eigenvectors, so linearly independent eigenvectors. I do this matrix multiplication and I end up with a matrix where all the eigenvalues are in a diagonal form. So QR method actually does a similar matrix multiplication, where instead of multiplying with P, it has got some certain specific matrix. When it multiplies that, let's say it calls that as P, or let's say Q inverse AQ, or Q inverse AQ on this form, what happens, everything, all the eigenvalues will actually lie in a diagonal form. So that basically helps to find the eigenvalues for any full rank matrix. Now, I just give you a very qualitative overview of these techniques because I don't want you to go into the details. If you are interested, you can also look at the algorithms that I mentioned, but I don't see that it is adding any new value to our discussion. So I'm just leaving that to only the qualitative discussion about what these techniques actually do. So qualitatively, this transformation helps to transform our matrix into a tri-diagonal system or upper Hessenberg matrix system, and then we apply QR method such that our eigenvalues all lie in a diagonal form, and we can extract the eigenvalues from there.